Hello students, in this video we're going to solve a first order linear ordinary differential equation. Remember first order because the highest order of the derivatives present is 1, so that is first order, and linear because all the terms in the dependent variable appear linearly, all the derivatives and the independent variable. Okay. So I'm going to make a simplifying assumption. I'm going to assume that this function y of t, we know it's a function of t because t is the independent variable. I'm going to assume it's greater than 0 for all t because I don't want to get bogged down in some analysis as we um, get along further in this problem. Okay, so I'm just going to assume that y of t is greater than 0 for all t. Okay, the first thing I'm going to do is I'm going to divide both sides by y. Of course, y being greater than 0 makes that step permissible. And then what I'm going to do is I'm going to integrate both sides. And I changed the variable here. Instead of t here, I made the dummy variable s, and then I made the upper limit of integration t, and I made the bottom limit some constant a. A is a real number. So I'm going to integrate both sides that way. And that way, if I make the upper limit of integration t, I will maintain that this is a function of t. Okay. So when I integrate both sides, watch what happens here. I integrate the right-hand side. You can ignore the left-hand side for a moment. And of course, I'm going to get s evaluated at t minus a. So then that would be just t minus a, right? Okay, on the left-hand side, I recognize what's going on here. And this looks like the chain rule just happened. I understand this is a bit of a clever realization here. And I'm going to give you two more methods for solving this ODE. One is called separation of variables, and the other is recognizing that's a linear equation. And so we'll use an integrating factor. But for this video, I just wanted to follow along with this line of reasoning so you could see where these natural logs are coming from. And I wanted to give you a sense of how we can make the method of separation of variables a little more rigorous. Anyhow, um, just reverse engineer this. If you take the derivative of the natural log, you get 1 over y, and then you have to take the derivative of the inside function. So there you go. It's just like implicit differentiation or the chain rule. Okay, well, if I integrate the derivative, then of course they unravel each other. So fundamental theorem of calculus says then I get the natural log of y of t, and that's why I made the upper limit of integration t. So now I have a function of t minus the natural log of y of a, and this natural log is well defined because once again y is greater than 0. All right, so that's all the calculus actually involved with this problem. So the next steps is just pushing some symbols around and doing some algebra. I push the natural log of y of a to the other side, and I collect that with the minus a. So here I have all the constant terms. So since that is a constant, I'm just going to call that CA. And then I'm going to exponentiate each side. So, pardon me. So the when I take the exponential of the natural log of y of t on the left-hand side, and then on the right-hand side, I have e to the t plus ca, which is that constant. I'm just going to use the laws of exponents. Whenever you add exponents, that means you must have multiplied the same bases. And then that just simplifies. The exponential and the natural log are inverse functions, so the y of t just drops down. The CA, I'm just going to call that a constant as well then. Okay, I'm going to call it a constant C. So I have ET times C, or I can put the C in the front, and I get the solution to this ordinary differential equation. You could verify that this is in fact a solution if you take the derivative of y with respect to t. The C factors out, and the derivative of e e to the t with respect to t is just e to the t back again. So in other words, you just get y back again. So once again, we've just shown that um, the exponential is the function who, if you take its derivative, you get the function back again. All right, good luck.